In the quiet landscapes of early 20th century Germany, as the world was moving from the age of steam into the electric hum of modernity, a young boy named Werner Heisenberg began to look at the world with a sense of wonder that few others could match. Born on December 5, 1901, in Würzburg, Heisenberg grew up in an environment filled with intellectual curiosity. His father, August Heisenberg, was a professor of Greek philology, a man devoted to ancient texts and classical learning, while his mother, Annie Wecklin, came from a family deeply connected to education. From the earliest years, Werner's surroundings were filled with books, ideas, and discussions about knowledge. Yet for young Werner, curiosity was never confined to the written word. It lived in the sounds of nature, in the patterns of the stars, and in the invisible order that seemed to guide the world around him. As a child, Heisenberg displayed a restless mind. He was drawn to puzzles, mathematical problems, and games of logic. While other children might have been content to play in the streets, Heisenberg often found joy in exploring the hidden structure of things. He would spend hours working through mathematical equations for the sheer pleasure of discovering patterns. This early fascination with the abstract hinted at a future shaped by deep intellectual pursuits. The sense of perfection, symmetry, and logic that mathematics offered resonated with his young mind. It gave him a way to make sense of the mysteries he saw around him, mysteries that would later evolve into the core of his life's work. The early 1900s were a time of great transformation in science and culture. Albert Einstein had already begun to redefine space and time with his theory of relativity. Max Planck had introduced the radical idea of energy quanta, a notion that energy was not continuous but came in discrete packets. These ideas were stirring the foundations of classical physics, but to a young Heisenberg, still years away from university, they were distant echoes, intriguing but abstract. He was still immersed in the world of numbers, geometry, and the beauty of logic. His world was one where every equation was a new way to understand the hidden harmony of nature. When Heisenberg entered secondary school in Munich, his intellect quickly stood out. Teachers described him as intensely focused, sometimes to the point of obsession. He thrived on competition and excellence. Mathematics became his language, a medium through which he could express the unspoken order of reality. He mastered complex concepts well beyond his age, finding in them not just solutions, but a kind of aesthetic pleasure. Yet, even as he excelled in his studies, Heisenberg's curiosity stretched beyond the boundaries of the classroom. He was fascinated by philosophy, by the deep questions of existence and knowledge. What does it mean to understand something? How do we know what is real? These philosophical thoughts intertwined with his love for science, forming the basis of a worldview that would guide him throughout his life. The Germany of Heisenberg's youth was marked by turbulence and change. The First World War was casting its long shadow over Europe, and social tensions were rising. Young Werner, still in his teenage years, witnessed the collapse of the old order and the birth of a new, uncertain world. During these times of turmoil, he found refuge in study and reflection. Mathematics and physics were, for him, a world of certainty amid chaos. The exactness of equations and the logic of natural laws offered stability in a time when everything else seemed to crumble. His academic achievements quickly attracted attention. He began to study advanced works by great mathematicians and physicists, immersing himself in the ideas that were transforming modern science. In particular, he was drawn to the works of Arnold Sommerfeld, a leading physicist at the University of Munich known for his rigorous approach to atomic theory. Sommerfeld's name would soon become central to Heisenberg's journey. But before that meeting could occur, Heisenberg had to navigate one of the most difficult chapters of his youth, the aftermath of the war. After Germany's defeat in 1918, the country fell into chaos. Economic collapse, political unrest, and revolutionary movements swept through the streets. Like many young men of his generation, Heisenberg was caught between idealism and despair. He briefly joined a youth movement known as the Freie Deutsche Jugend, a group that sought to rebuild moral and cultural values in the face of national destruction. These young idealists believed in a return to simplicity, discipline, and nature, ideas that appealed deeply to Heisenberg's sense of order and ethics. It was during these years that he developed a lifelong appreciation for music, philosophy, and the natural world. He learned that science was not merely a technical pursuit, but part of a broader search for harmony and meaning in life. By the time Heisenberg entered the University of Munich in 1920, he was already recognized as a prodigious student. He joined Sommerfeld's theoretical physics group, one of the most prestigious in Europe. Sommerfeld was known not only for his brilliance but also for his ability to identify and nurture young talent. Under his mentorship, Heisenberg found the perfect environment to channel his intellectual energy. The discussions in Sommerfeld's seminar were intense and wide-ranging, touching upon the latest developments in atomic theory, relativity, and the mysteries of quantum phenomena. Heisenberg thrived in this environment of creative tension. He would often challenge existing assumptions, asking questions that seemed simple but led to profound insights. His early years in academia were defined by a deep commitment to clarity and precision. He rejected vague interpretations of physical reality and insisted that science must deal only with measurable quantities. This idea would later become central to his development of quantum mechanics. Even as a young student, Heisenberg's thinking was guided by a belief that nature reveals itself not through what we imagine, but through what we can observe and calculate. His approach was both logical and radical, a combination that would one day change the course of physics. Heisenberg's curiosity often pushed him beyond conventional boundaries. During his studies, he visited Göttingen, where he met Max Born, another towering figure in theoretical physics. Born immediately recognized Heisenberg's potential and invited him to work on problems related to atomic structure. The collaboration between Born and Heisenberg was more than academic, it was a meeting of minds that shaped the future of science. Under Born's influence, Heisenberg began to explore new ways of representing atomic systems, ways that did not rely on visualizing electron orbits but on mathematical relationships. Despite his growing confidence, Heisenberg often struggled with the limitations of classical theory. The atomic models of the time, particularly Niels Bohr's planetary model, failed to fully explain experimental data. Heisenberg's instinct told him that something deeper was missing, something hidden beneath the surface of equations. He began to question the very foundations of how physicists described reality. These questions led him to one of the most significant turning points in his career, his time at Bohr's Institute for Theoretical Physics in Copenhagen. In 1924, Heisenberg traveled to Copenhagen to work with Niels Bohr, a man whose insights into atomic structure had already made him a legend. Bohr's Institute was a place where the boundaries of physics were constantly being challenged. For Heisenberg, this was not just a laboratory, it was a temple of thought. The discussions there were fierce, filled with philosophical depth and scientific daring. Bohr's emphasis on complementarity, the idea that particles could exhibit both wave-like and particle-like properties, resonated deeply with Heisenberg's evolving views. Together, they sought to uncover the language that could describe the strange and unpredictable world of the atom. Heisenberg's time in Copenhagen was transformative. He learned to balance intuition with mathematics, philosophy with experiment. He discovered that the quest to understand the atom was also a quest to understand knowledge itself. Every conversation, every calculation brought him closer to the realization that the world of particles could not be described in the same way as the world of everyday experience. The subatomic realm was governed by principles that defied classical logic. As the months passed, Heisenberg became increasingly obsessed with finding a consistent theory that could describe atomic behavior. His health often suffered from overwork. He would spend nights without sleep, immersed in equations and calculations. During one summer on the island of Helgoland, plagued by hay fever but driven by determination, Heisenberg finally achieved the breakthrough that would define his life. There, isolated from distractions, he reformulated the mechanics of the atom using pure mathematics without relying on visual images of electron orbits. This new formulation, matrix mechanics, became the first complete version of quantum mechanics. But that moment of discovery still lay in the near future. In the years leading up to it, Heisenberg's mind was being sharpened by every challenge he faced. The long nights of study in Munich, the intellectual battles in Göttingen, and the philosophical discussions in Copenhagen, all these experiences molded him into the scientist he would become. His early curiosity had evolved into a disciplined pursuit of truth, a search that combined logic, creativity, and a deep sense of wonder. By his early 20s, Werner Heisenberg was no longer merely a student, he was a rising star in the scientific world. His reputation for brilliance spread quickly, but it was his relentless curiosity that truly set him apart. He was not content with solving problems. He wanted to understand the meaning behind them. What did it mean that particles behaved as both waves and matter? Why did nature seem to hide its workings behind probabilities rather than certainties? These questions haunted him, but they also fueled his imagination. Heisenberg's rise as a physicist was not simply the story of a young genius ascending through talent and hard work. It was the story of a man who saw science as a spiritual quest, a way to glimpse the hidden order of the universe. His early years were defined by a belief that beneath the complexity of the world lay a simple, elegant truth, a truth that could be expressed through the language of mathematics. This belief, nurtured since his boyhood days in Würzburg, would guide him toward discoveries that forever changed humanity's understanding of the atom and the limits of knowledge itself. His journey from a curious child fascinated by puzzles to a physicist standing on the threshold of quantum theory was a journey of both intellect and spirit. The young Werner Heisenberg had not yet articulated the uncertainty principle, but its seeds were already growing within him. The realization that the more deeply we seek to understand the universe, the more we confront the boundaries of what can be known, and in those boundaries he found not frustration, but beauty. In the years following his return from Copenhagen, Werner Heisenberg stood at the edge of a new world, one that only a handful of scientists could even glimpse. The 1920s were a golden age for theoretical physics, a time when familiar rules were breaking apart and new ones were emerging from the chaos. In the laboratories and universities of Europe, old assumptions about matter, energy, and motion were being questioned. To many, this was unsettling. To Heisenberg, it was exhilarating. He had come to believe that the deepest truths of nature could not be grasped by imagination alone. They had to be expressed in mathematical relationships, stripped of the illusions that human senses create. By 1925, Heisenberg's thoughts had reached a fever pitch. He could no longer tolerate the inconsistencies of Bohr's atomic model or the half measures of existing quantum theories. The idea that electrons orbited the nucleus like planets around the sun seemed elegant, but experiment after experiment showed that this image was deeply flawed. The behavior of light, the discrete energy levels of atoms, and the strange patterns in spectral lines, none of it made sense under the laws of classical mechanics. Heisenberg decided to abandon visualization altogether. If one could not truly see the inner workings of the atom, then perhaps one should stop trying to picture them. That summer, seeking isolation and relief from his chronic hay fever, Heisenberg retreated to the rocky island of Helgoland in the North Sea. The island was windswept and bare, surrounded by restless waves. For Heisenberg, it became a refuge, a place where he could escape both the physical irritations of pollen and the intellectual noise of academic debate. He spent his days walking along the cliffs and his nights immersed in calculation, scribbling equations under the dim light of a lamp. Alone with his thoughts, he tried to reimagine atomic physics from the ground up. What he eventually wrote down in his notebooks that summer would mark the birth of a new physics. Instead of describing the motion of electrons as paths through space, Heisenberg represented their behavior as arrays of numbers, tables of quantities that captured how one measurable state could transform into another. These numerical tables, or matrices, had strange properties when multiplied. They did not follow the familiar rules of arithmetic, yet they perfectly matched the experimental data. What Heisenberg had discovered, though he did not realize it at first, was the foundation of matrix mechanics, the first complete formulation of quantum mechanics. When Heisenberg returned to Göttingen and showed his results to Max Born, Born immediately recognized the mathematical form of matrices in Heisenberg's work. With the help of his student Pascual Jordan, Born translated Heisenberg's abstract notes into formal equations. The collaboration between these three scientists produced one of the most profound papers in the history of science. It described a world where observables like position and momentum were no longer precise quantities but elements of mathematical structures that encoded probabilities. Reality itself had become a set of relationships, measurable but not entirely knowable. The publication of Heisenberg's paper in 1925 stunned the scientific community. For decades, physicists had relied on intuition and visualization to understand the natural world. Heisenberg's approach was unapologetically abstract, stripped of imagery, rooted purely in calculation. Many resisted it at first, unable to accept a vision of nature that seemed so detached from the senses. Yet others, including Niels Bohr, saw in it the first true path to understanding the quantum world. As quantum mechanics began to take shape, it became clear that Heisenberg's ideas had transformed the language of physics. But his greatest conceptual leap was still to come. In 1927, while exploring the implications of his equations, Heisenberg realized something extraordinary: that there was a fundamental limit to how much one could know about a particle's properties. The more precisely one measured an electron's position, the less precisely one could determine its momentum, and vice versa. This was not due to flaws in instruments or human error. It was a property of nature itself. This insight crystallized into the uncertainty principle, a revelation that shattered centuries of deterministic thinking. Since Newton, science had assumed that if one knew the exact conditions of a system, one could predict its future with perfect accuracy. Heisenberg showed that this dream of certainty was an illusion. At the subatomic level, nature did not operate according to strict cause and effect. Instead, it unfolded in probabilities, waves of possibility collapsing into reality only when observed. The uncertainty principle did more than redefine physics, it redefined philosophy. It forced humanity to confront the limits of knowledge and the role of the observer in shaping reality. Heisenberg himself struggled with its implications. He was a deeply thoughtful man, trained not only in mathematics but also in classical philosophy. He saw in his discovery a reflection of ancient ideas: that the act of knowing changes the thing known, that nature hides her secrets behind a veil that can never be fully lifted. Bohr, ever the philosopher, embraced the uncertainty principle as part of his own idea of complementarity. The notion that wave and particle, certainty and uncertainty, are not contradictions but two perspectives on the same truth. Together, Bohr and Heisenberg debated endlessly, sometimes passionately, about what their discoveries meant. Their discussions were not merely technical, they were existential. In the quiet rooms of the Copenhagen Institute, they pondered questions that blurred the line between physics and metaphysics. What is reality before it is measured? Does the universe exist independently of observation? Heisenberg's rise to prominence was swift. In 1932, at the age of 31, he received the Nobel Prize in Physics for his creation of quantum mechanics. He had become one of the youngest Nobel laureates in history. The award recognized not only his brilliance but also his courage, the willingness to abandon intuition and embrace abstraction in the search for truth. Yet fame never seemed to change Heisenberg. He remained modest, disciplined, and intensely focused on the deeper meaning of his work. To him, physics was not just a profession, it was a moral and intellectual calling. But the years that followed were darkened by the rise of Nazism. As Hitler came to power in 1933, Germany's scientific community was torn apart by ideology. Many of Heisenberg's colleagues, including Jewish scientists like Albert Einstein, were forced into exile. Heisenberg chose to stay in Germany, hoping to protect what remained of its academic tradition. It was a decision that would haunt him for the rest of his life. During the Second World War, Heisenberg found himself at the center of a moral storm. He was appointed to lead the German uranium project, research that could have led to the development of an atomic bomb. Whether he truly sought to build such a weapon or quietly resisted the idea remains a subject of debate. Some historians believe he intentionally slowed the project, ensuring it would never succeed. Others argue that he simply miscalculated the technical requirements. Whatever the truth, Heisenberg's wartime actions became a shadow that followed him long after the guns fell silent. After Germany's defeat, Heisenberg was captured by Allied forces and interned in England as part of Operation Epsilon. There, in a secluded country house at Farm Hall, he and other German scientists were secretly recorded as they discussed the atomic bombings of Hiroshima and Nagasaki. When Heisenberg heard the news, he was initially skeptical, believing it impossible that such a weapon could have been built. His astonishment at the reality of the atomic bomb revealed both his ignorance of the Manhattan Project's progress and his own moral unease. In the post-war years, Heisenberg dedicated himself to rebuilding German science and restoring its moral integrity. He became a leading figure in the creation of new research institutions, including the Max Planck Institute for Physics. He traveled widely, lecturing on both physics and philosophy, speaking not only of equations but of ethics, responsibility, and the relationship between knowledge and power. He believed that science, like all human endeavors, must serve humanity rather than dominate it. His writings from this period reveal a profound thinker grappling with the meaning of uncertainty beyond the laboratory. To Heisenberg, the uncertainty principle was not a limitation but a lesson in humility. It reminded humankind that knowledge has boundaries, that the universe resists complete understanding. In this sense, Heisenberg's physics became a metaphor for life itself, a recognition that even in our greatest achievements, mystery remains. As he grew older, Heisenberg continued to explore new ideas, including attempts to unify quantum theory and relativity. Though these later efforts were less successful, they demonstrated his lifelong refusal to rest on past achievements. He remained a seeker, guided by the same curiosity that had driven him as a boy. His colleagues remembered him as a man of quiet intensity, equally comfortable discussing mathematics or playing back on the piano. Music had always been a refuge for him, another expression of harmony and order. Just as in physics, he found in music the balance between structure and freedom, between certainty and emotion. By the time of his death in 1976, Werner Heisenberg had become a symbol of both genius and introspection. His discoveries had transformed science, leading to technologies that defined the modern world: semiconductors, lasers, nuclear energy, and the first steps toward quantum computing. Yet he remained above all a philosopher of nature. He saw in the atom not a source of power, but a window into the profound mystery of existence. The story of Heisenberg's early curiosity and rise as a physicist is not simply a tale of equations and discoveries. It is a human story of wonder, ambition, doubt, and moral struggle. From the quiet classrooms of Munich to the wind-swept island of Helgoland, from the brilliant halls of Copenhagen to the uncertain shadows of wartime Germany, Heisenberg's life traced the path of a man forever searching for the hidden order of the world. He sought to unlock the secrets of the atom, and in doing so, he unlocked something even deeper: the realization that the quest for knowledge is inseparable from the limits of human perception. His uncertainty principle stands today, not only as a pillar of modern physics, but as a reminder that in the face of the unknown, humility and curiosity must coexist. The more we learn, Heisenberg taught us, the more we must accept that some part of reality will always remain beyond our grasp. In that truth lies both the challenge and the beauty of science. For it is the mystery that drives discovery, the uncertainty that fuels the human spirit to keep exploring. Werner Heisenberg's early curiosity never faded, it simply evolved into a lifelong dialogue with the universe, one that continues to echo in every laboratory, every equation, and every mind that dares to ask, what lies beyond what we can see? In the early decades of the 20th century, the world of science stood on the edge of a revolution. The grand edifice of classical physics, built over centuries by giants like Newton, Maxwell, and Boltzmann, had begun to tremble under the weight of strange new discoveries. For hundreds of years, physicists had believed that nature could be described with perfect precision. That if one knew the initial conditions of a system, its future could be predicted with certainty. The universe was viewed as a great machine, governed by laws of cause and effect, its behavior predictable to the last detail. Yet, beneath this comforting order, a series of unsettling observations was beginning to whisper that reality was far more mysterious than anyone had imagined. By the dawn of the 20th century, the smallest building blocks of matter, atoms, were no longer thought of as indivisible. Experiments with cathode rays, X-rays, and radioactivity had revealed that atoms themselves contained smaller particles, electrons, protons, and later, neutrons. The discovery of these subatomic components opened a new frontier, but it also brought chaos. The elegant equations of classical mechanics could not explain the peculiar behaviors observed inside the atom. When physicists tried to apply Newton's laws to the motion of electrons, their predictions failed spectacularly. The atom, it seemed, refused to obey the rules of common sense. One of the first cracks in the old order came from an unexpected place: the study of heat radiation. In 1900, the German physicist Max Planck was trying to solve a simple problem: how objects emit light and heat. Classical theory predicted that as an object was heated, it should radiate infinite energy at short wavelengths, a result so absurd it was called the ultraviolet catastrophe. To fix this, Planck proposed a radical idea: energy was not continuous but came in discrete packets, or quanta. It was a mathematical trick, a desperate attempt to make the numbers work. Yet, without realizing it, Planck had laid the first stone of quantum theory. He had introduced a constant, now known as Planck's constant, that defined the smallest possible unit of action in the universe. At first, Planck's idea was regarded as an oddity. Even he did not fully believe in the physical reality of quanta. But in 1905, a young patent clerk named Albert Einstein took the idea seriously. He used it to explain the photoelectric effect, the mysterious way light could knock electrons out of metal surfaces. Einstein proposed that light itself was made up of particles, which he called photons. This was a direct challenge to the long-held belief that light was purely a wave. With that single insight, Einstein cracked open the door to a new physics where energy, matter, and light existed in dual and seemingly contradictory forms. Meanwhile, in the laboratories of Europe, experiments were piling up that defied explanation. Niels Bohr, a Danish physicist, took Planck's and Einstein's ideas and used them to create a model of the atom in 1913. In Bohr's vision, electrons orbited the nucleus in fixed energy levels, jumping between them by absorbing or emitting discrete quanta of energy. The model explained the spectral lines of hydrogen, the distinct colors of light emitted by excited atoms. But it was incomplete. It could describe the hydrogen atom beautifully, yet it could not be extended to more complex elements. The Bohr model was a fragile bridge between the old and the new, a temporary truce between classical intuition and quantum reality. Throughout the 1910s and early 1920s, the scientific world struggled to reconcile experiment with theory. Louis de Broglie, a young French prince turned physicist, proposed another revolutionary idea: if light could behave like a particle, perhaps particles like electrons could behave like waves. This symmetry between matter and energy suggested a universe far stranger than anyone had anticipated. But even as these ideas multiplied, There was no unified theory to explain how matter and energy truly behaved on the atomic scale. It was in this period of confusion and creativity that Werner Heisenberg emerged as one of the leading figures of a new generation. A brilliant young physicist from Germany, Heisenberg was deeply frustrated by the limitations of existing models. He was not content with patching together old ideas to fit new data. He wanted a theory that would describe what could actually be measured, not what could be imagined. He had grown wary of visualizing electrons as tiny planets orbiting a miniature sun. The mathematics did not work, and the experiments refused to cooperate. For Heisenberg, the path forward lay not in picturing the invisible, but in stripping away all pictures entirely. In the summer of 1925, suffering from severe hay fever and mental exhaustion, Heisenberg retreated to the island of Helgoland in the North Sea. The island's stark cliffs and endless winds offered isolation from both pollen and distraction. There, surrounded by the rhythm of the waves and the cries of seabirds, Heisenberg began to rebuild physics from the ground up. Working late into the night, he focused only on quantities that could be directly observed, the frequencies and intensities of light emitted by atoms. What he produced over those sleepless nights was a set of equations unlike any that had come before. They ignored the imagined paths of electrons and focused purely on measurable relationships. When Heisenberg presented his work to Max Born upon returning to Göttingen, Born immediately recognized the mathematical structure hidden within it, the mysterious world of matrices. Born, along with his student Pascual Jordan, formalized Heisenberg's insight into a consistent theory matrix mechanics. This new framework was abstract, unfamiliar, and deeply unintuitive. Yet, for the first time, it made accurate predictions about the behavior of atoms. Matrix mechanics was the first full formulation of quantum mechanics, a theory that would soon redefine all of physics. It described a world where the properties of particles were not fixed values but probabilities, and where observation itself played a fundamental role in shaping reality. For Heisenberg, it was the realization of a dream, a physics built on certainty about what could be measured and humility about what could not. At nearly the same time, across Europe, another brilliant mind was working along a different path toward the same destination. In Austria, the physicist Erwin Schrödinger sought a more visual, continuous description of the quantum world. Inspired by de Broglie's idea of matter waves, Schrödinger developed a new equation that treated electrons not as discrete particles, but as wave-like entities spread out in space. His wave mechanics offered a picture of the atom that felt more intuitive, smoother, and more compatible with the mathematical traditions of classical physics. At first, these two versions of quantum mechanics, Heisenberg's matrix mechanics and Schrödinger's wave mechanics, seemed utterly different. One dealt in abstract arrays of numbers, the other in graceful undulating waves. Yet, as Schrödinger and others soon demonstrated, they were mathematically equivalent, two faces of the same mysterious reality. The tension between them mirrored the very nature of the quantum world, a duality that defied simple description. The unification of these ideas marked one of the most profound revolutions in the history of science. The familiar certainties of Newton's universe dissolved into a realm of probabilities, where cause and effect gave way to chance and possibility. Quantum mechanics did not merely describe the atomic world, it revealed a universe that was fundamentally indeterminate. For many scientists, this realization was deeply unsettling. Albert Einstein, who had helped to spark the quantum revolution, now found himself opposing it. He could not accept that nature operated by chance. God does not play dice, he famously declared. To Einstein, the indeterminacy of quantum mechanics was a sign that the theory was incomplete. But for Heisenberg, Born, and others, this was not a flaw, it was the truth revealed by nature itself. The debates that followed between Einstein and Bohr became legendary. Einstein devised thought experiments to expose what he saw as weaknesses in quantum mechanics. Bohr countered each one with relentless precision, defending the principle that measurement defines reality. Heisenberg, caught between the two giants, found himself more convinced than ever that uncertainty was not a defect but a fundamental feature of existence. By the late 1920s, quantum mechanics had become the cornerstone of modern physics. Its equations explained not only the structure of atoms, but also the behavior of molecules, the mechanisms of chemical bonding, and the spectra of light. It provided the foundation for technologies that would shape the 20th century, from transistors and semiconductors to lasers and nuclear energy. But beyond its practical applications, quantum mechanics represented a profound shift in humanity's understanding of the universe. No longer could scientists claim that observation was passive. The very act of measuring a system altered its state. The observer and the observed were entangled, bound together in a web of interaction. Reality itself appeared to be participatory, not a fixed stage, but a dynamic process in which knowledge and existence intertwined. This new vision of nature carried deep philosophical implications. It suggested that at the most fundamental level, the universe is not composed of solid, independent things but of possibilities, relationships, and probabilities. The line between certainty and uncertainty, between cause and effect, blurred into a delicate balance. The quantum revolution had not only rewritten the laws of physics, it had redefined what it meant to know. For Heisenberg and his contemporaries, these discoveries were both exhilarating and humbling. They had opened the door to a world where matter and energy, wave and particle, knowledge and mystery, coexisted in a delicate and eternal dance. The journey from Planck's quanta to Heisenberg's uncertainty was not just a scientific evolution. It was a transformation of human thought itself. As the 1920s came to a close, the old vision of the universe as a predictable machine lay in ruins. In its place stood a new vision, one alive with potential, governed by probabilities, and illuminated by the flickering light of uncertainty. The revolutionary birth of quantum mechanics was not merely the creation of a new theory, it was the awakening of a new way of seeing reality. And at its heart were the young, restless minds who dared to question everything, to look beyond the visible, and to find truth in the invisible patterns of the atom. In the years following the initial formulation of quantum mechanics, the world of physics was forever transformed. The abstract equations of matrix mechanics and the wave equations of Schrödinger no longer existed as mere curiosities or theoretical exercises. They had become the new framework for understanding the very fabric of reality. Scientists across Europe and the United States rushed to explore the implications of these revolutionary ideas. Laboratories buzzed with activity, as experiments once thought impossible were attempted, and theoretical predictions were tested with increasing precision. The strange, probabilistic world described by Heisenberg, Bohr, Born, and Schrödinger was no longer a matter of abstract speculation. It was becoming the foundation of a scientific reality that could be measured, calculated, and applied. The intellectual climate of the late 1920s and 1930s was one of both excitement and controversy. Many physicists struggled to reconcile the new quantum mechanics with the intuitive, deterministic worldview of classical physics. The notion that particles could behave as both waves and particles, that certainty could be replaced by probability, challenged centuries of established thinking. Yet, experiments continued to confirm the predictions of quantum theory. Phenomena such as the splitting of spectral lines in magnetic fields, the behavior of electrons in crystals, and the peculiarities of atomic spectra all conform to the probabilistic patterns dictated by the new mathematics. Quantum mechanics was not merely a theoretical curiosity, it was a practical tool that revealed the hidden order of nature. Heisenberg's uncertainty principle, formulated in 1927, became a cornerstone of this new framework. It formalized the idea that at the atomic level, certain pairs of physical properties, such as position and momentum, could not be simultaneously known to arbitrary precision. This was not a limitation of measurement techniques or instruments, it was an intrinsic property of nature itself. The principle shook the foundations of classical physics, suggesting that the universe was not a deterministic clockwork, but a realm governed by probability and uncertainty. This realization sparked debates not only in physics but also in philosophy. Questions of causality, reality, and the limits of human knowledge took center stage in scientific discourse. Across Europe, young physicists were captivated by the new theory. Niels Bohr's Institute in Copenhagen became a hub of intellectual activity, drawing brilliant minds from around the world. Here, Heisenberg, Bohr, and others engaged in rigorous discussions, often lasting late into the night. They debated the meaning of the equations, the role of observation, and the philosophical implications of quantum mechanics. These debates were not mere academic exercises, they shaped the direction of research and the interpretation of results. The famous Bohr-Heisenberg dialogues exemplified the tension between intuition and mathematics, between the desire for visualizable models and the necessity of abstract formalism. Meanwhile, the new theory began to influence other areas of physics and chemistry. The understanding of atomic and molecular structures allowed chemists to predict chemical reactions with unprecedented accuracy. The development of quantum theory also laid the groundwork for the emerging field of solid-state physics, which would later give rise to semiconductors, transistors, and ultimately modern electronics. In essence, the revolution in theoretical physics was already beginning to ripple through technology, reshaping the world in ways that its creators could scarcely have imagined. Despite these successes, the philosophical implications of quantum mechanics were deeply unsettling for many. Albert Einstein, who had contributed to the early foundations of quantum theory, remained skeptical. He famously remarked, "God does not play dice," expressing his discomfort with the idea that probability, rather than determinism, governed the universe. Einstein believed that quantum mechanics, while highly successful in predicting experimental outcomes, could not provide a complete description of reality. The ensuing debates between Einstein and Bohr became legendary, representing a clash not only of theories but of worldviews. Bohr argued that quantum mechanics was complete and that uncertainty and probability were fundamental features of nature, not flaws in the theory. These debates highlighted the profound intellectual and philosophical challenges posed by the new physics. In parallel, the mathematical formalism of quantum mechanics continued to evolve. Dirac, Jordan, von Neumann, and other theorists refined the equations, developed new representations, and extended the theory to include spin, relativistic effects, and interactions among multiple particles. The mathematical structure became increasingly sophisticated, and with each advance, the theory's predictive power grew. Quantum mechanics was no longer a collection of isolated ideas. It had become a coherent framework capable of explaining a vast range of phenomena, from the behavior of electrons in atoms to the properties of solids and the interactions of light with matter. The impact of quantum mechanics extended far beyond the laboratory. It reshaped the way scientists thought about causality, measurement, and the very nature of reality. The classical notion of an objective universe, where properties existed independently of observation, was replaced by a vision in which the observer played a crucial role. Reality at the quantum level became participatory. The act of measurement affected the system being measured, linking knowledge and existence in an inseparable way. This realization had profound implications not only for physics but also for philosophy, influencing thinkers in fields as diverse as epistemology, metaphysics, and even psychology. By the 1930s, quantum mechanics had become firmly established, and its principles were being applied to increasingly complex systems. Heisenberg and his colleagues were exploring the behavior of multi-electron atoms, nuclear interactions, and the emerging field of particle physics. The revolutionary framework they had created provided the tools to probe deeper into the structure of matter than ever before. Experiments confirmed the predictions of quantum theory with astonishing precision, solidifying its status as one of the most successful scientific theories in history. At the same time, the rise of totalitarian regimes in Europe posed new challenges for scientists. Many physicists, particularly those of Jewish heritage, were forced to flee Germany and other countries, while those who remained faced moral and ethical dilemmas. Heisenberg, who continued his work in Germany, found himself navigating a complex landscape, balancing scientific ambition with ethical responsibility. These years tested not only the intellect, but also the character of the scientific community. The revolutionary birth of quantum mechanics, which had begun as a purely theoretical endeavor, now intersected with global events in ways that underscored the profound societal implications of scientific discovery. The global spread of quantum mechanics transformed the scientific landscape. Universities and research institutions across Europe, the United States, and Asia embraced the new theory. Young physicists trained in the principles of matrix mechanics and wave mechanics carried the revolution forward, expanding its applications and refining its mathematical underpinnings. The collaborative, international nature of quantum research fostered an unprecedented exchange of ideas, setting the stage for the technological and scientific advances of the mid-20th century. Quantum mechanics also inspired a generation of thinkers to explore the philosophical consequences of a probabilistic universe. Questions about determinism, causality, and the role of the observer became central topics of debate not only among physicists, but also among philosophers and intellectuals worldwide. The realization that certainty was limited at the most fundamental level challenged long-held assumptions about knowledge, reality, and human understanding. The revolutionary birth of quantum mechanics had, in effect, rewritten the rules of both science and thought. As the 1930s progressed, the applications of quantum mechanics began to extend into practical technology. Understanding the behavior of electrons in atoms and solids led to advances in spectroscopy, chemical analysis, and the design of new materials. The theoretical insights provided by Heisenberg, Schrödinger, and their contemporaries laid the foundation for the development of semiconductors, magnetic resonance techniques, and ultimately, the digital revolution. The seemingly abstract equations of matrix mechanics and wave mechanics were becoming tangible forces shaping the modern world. Yet, for all its practical implications, the revolutionary birth of quantum mechanics was first and foremost a story of human imagination and intellectual courage. It was a story of scientists willing to abandon centuries of classical intuition, to embrace uncertainty, and to create a framework that captured the hidden order of nature. It was a story of minds capable of thinking in ways that transcended everyday experience, of seeing patterns in chaos, and of uncovering the invisible structures that govern reality. Heisenberg, in particular, exemplified this combination of brilliance and philosophical depth. His insistence on focusing only on what could be observed, measured, and calculated was more than a methodological choice. It was a reflection of a profound understanding of the limits of knowledge. By embracing abstraction, by letting go of familiar imagery, he and his colleagues were able to penetrate the mysteries of the atom and lay the groundwork for a scientific revolution that continues to shape the modern world. The revolutionary birth of quantum mechanics was not merely the development of a new set of equations. It was a transformation of human understanding, a shift in perspective that challenged everything previously taken for granted about the nature of reality. From Planck's quanta to Heisenberg's matrices, from Einstein's photons to Schrödinger's waves, the journey of discovery was marked by courage, creativity, and an unyielding commitment to truth. The world of the atom had revealed itself to be far stranger and more wondrous than anyone could have imagined, and in doing so, it reshaped the very way humans perceive the universe. In the late 1920s, as quantum mechanics began to take shape, a profound realization emerged from the work of Werner Heisenberg, one that would challenge not only physics, but the very way humanity understood reality. It was during this period, in the midst of intense mathematical investigation and philosophical contemplation, that Heisenberg formulated what would become known as the uncertainty principle. This principle, deceptively simple in its statement yet profound in its implications, declared that there are fundamental limits to what can be known about certain pairs of physical properties of a particle, such as its position and momentum. It was not a limitation of experimental tools or human ingenuity, it was a limitation built into the fabric of nature itself. Heisenberg's insight did not emerge in isolation. The scientific community of the 1920s was grappling with a series of anomalies that classical physics could not explain. Spectral lines of atoms, the behavior of electrons in magnetic fields, and the dual nature of light as both particle and wave had already forced physicists to reconsider the foundations of their science. Heisenberg, deeply influenced by the rigorous mathematical training of the German academic tradition and the philosophical discussions with Niels Bohr in Copenhagen, began to focus on the practical limits of measurement. He asked a question that would become central to modern physics. How precisely can we know the properties of a subatomic particle when the act of observation itself disturbs it? The problem was deceptively simple in its formulation. Classical physics assumed that a particle had a definite position and momentum at every moment in time, and that, with sufficient precision, these quantities could be measured simultaneously. If one knew both precisely, one could predict the future behavior of the particle with absolute certainty. Yet, experiments in the early 20th century showed that this assumption failed at the atomic scale. Electrons and other subatomic particles exhibited behavior that seemed random, probabilistic, and fundamentally elusive. Heisenberg realized that this was not a failure of measurement but a property of nature itself. In 1927, Heisenberg formalized this understanding into the uncertainty principle. He mathematically demonstrated that the more precisely one measures a particle's position, the less precisely one can know its momentum, and vice versa. This was not a technical challenge, it was a statement about the intrinsic nature of reality. The principle was encapsulated in a simple inequality, but the philosophical reverberations were immense. For the first time, physics was telling humanity that certainty, long regarded as a cornerstone of scientific understanding, had intrinsic limits. The immediate implications for physics were dramatic. Classical mechanics, the framework that had described motion and forces for centuries, assumed determinism that with sufficient knowledge, one could predict the future with absolute confidence. The uncertainty principle shattered that assumption at the quantum level. In place of determinism arose a world governed by probabilities. Particles no longer had precise trajectories, instead, they existed in clouds of probability, described by wavefunctions that only collapsed into definite outcomes when observed. The universe, at its most fundamental level, was not a predictable clockwork but a realm of potentialities and chance. The scientific community initially met Heisenberg's principle with a mixture of awe and unease. Many physicists, including Albert Einstein, found it deeply unsettling. Einstein famously remarked, "God does not play dice," expressing his discomfort with the idea that nature could be fundamentally probabilistic. Yet, experimental evidence increasingly confirmed the predictions of quantum mechanics, including the uncertainty principle. Physicists began to accept that nature did not conform to human intuition, and that the limits of knowledge were not merely practical, but inherent. Heisenberg's principle also had profound implications for the philosophical interpretation of science. It blurred the line between the observer and the observed. In classical physics, measurement was considered a passive act. The observer could study a system without affecting it. In the quantum realm, the act of measurement itself influences the system. The uncertainty principle revealed that the observer and the observed are inextricably linked, challenging centuries of assumptions about objectivity and reality. Knowledge was no longer a simple reflection of the external world, it was a participatory act that shaped the very phenomena being studied. Beyond physics, the uncertainty principle resonated with broader philosophical and cultural currents. In an era marked by rapid technological and social change, it mirrored growing recognition that certainty and control are illusions. Philosophers, writers, and artists found in quantum mechanics a metaphor for the unpredictable and interconnected nature of reality. The principle suggested a universe where boundaries were porous, where knowledge was provisional, and where the search for understanding required humility as much as intellect. It became a symbol of the limits of human perception and the infinite complexity of the natural world. Heisenberg himself reflected deeply on the philosophical dimensions of his discovery. He was not content to leave it as a mere technical result in the equations of quantum mechanics. He saw in the uncertainty principle a bridge between science and human understanding, a reminder that the pursuit of knowledge is inseparable from reflection on its limits. He wrote and spoke extensively about the ethical and intellectual responsibilities of scientists, emphasizing that understanding the universe entails recognizing the boundaries of that understanding. Knowledge, he suggested, carries with it the imperative of humility. The principle also transformed experimental science. It forced physicists to rethink the design of experiments and the interpretation of data. Classical concepts such as the precise orbit of an electron around a nucleus were abandoned in favor of probabilistic models. Instruments could no longer be thought of as merely extending human senses; they became active participants in the phenomena being observed. The uncertainty principle guided the development of new experimental techniques, influencing fields from atomic physics to particle physics, and laying the foundation for technologies such as electron microscopes and quantum computing. Heisenberg's insight also sparked debates that went far beyond physics laboratories. Philosophers questioned the nature of reality, determinism, and free will in light of a universe that was fundamentally probabilistic. The uncertainty principle challenged long-standing notions of causality, suggesting that events at the smallest scales are not predetermined but contingent. This shift had implications not only for science but for human understanding of existence, prompting reflections on the nature of knowledge, the limits of certainty, and the role of human agency in the unfolding of events. As quantum mechanics matured, the uncertainty principle became a central tenet of the theory, interwoven with other key concepts such as wave-particle duality and complementarity. It provided a unifying framework that explained phenomena across a vast range of scales, from the behavior of electrons in atoms to the interactions of photons and the dynamics of subatomic particles. Its predictive power was confirmed repeatedly through experiments, cementing its status as one of the most profound insights in modern physics. Despite its abstract nature, the uncertainty principle has tangible consequences in the real world. It underpins the stability of atoms, the behavior of semiconductors, and the principles of quantum cryptography. The technological revolution of the 20th century, from lasers to MRI machines to quantum computers, is rooted in the same understanding that Heisenberg articulated nearly a century ago. What was once a purely theoretical insight has become a cornerstone of modern technology, shaping the very fabric of contemporary life. Culturally, the uncertainty principle has inspired generations to rethink the nature of knowledge and existence. Writers, philosophers, and artists have drawn upon its insights to explore themes of ambiguity, interconnectedness, and the limits of perception. The principle resonates beyond science, offering a metaphor for the unpredictable, complex, and interdependent nature of reality. It challenges human arrogance, reminding us that the universe does not yield all its secrets, and that the pursuit of understanding is an ongoing journey, rather than a destination. Heisenberg's work on the uncertainty principle also influenced the next generation of physicists, encouraging them to explore ever deeper questions about the quantum world. Figures such as Richard Feynman, Murray Gell-Mann, and John Bell built upon these foundations, developing new theories and experiments that continue to expand our understanding of the universe. The principle remains central to quantum theory, guiding both theoretical exploration and practical application, and serving as a reminder of the revolutionary insights that emerged from the study of the atom. Ultimately, the uncertainty principle represents more than a mathematical relationship. It is a profound statement about the nature of reality and the human endeavor to understand it. It tells us that certainty has limits, that observation shapes phenomena, and that knowledge is always intertwined with the act of discovery. It embodies the marriage of science and philosophy, demonstrating that the pursuit of truth requires both rigorous logic and deep reflection. In the story of modern physics, the uncertainty principle stands as a testament to the power of human intellect and imagination, a beacon illuminating the profound mystery at the heart of the quantum world. In the decades since its formulation, the uncertainty principle has maintained its central role in physics and philosophy. It continues to challenge assumptions, inspire debate, and fuel exploration. It reminds us that even in the age of advanced technology and sophisticated experimentation, nature retains a veil of mystery. Heisenberg's insight into the limits of knowledge reshaped science forever, creating a framework in which questions are as important as answers, and where the act of seeking understanding is as significant as the knowledge itself. In the years that followed the formulation of the uncertainty principle, its implications began to reverberate across the scientific community and beyond, transforming the way physicists approached both theory and experiment. The principle, which at first seemed like an abstract mathematical limitation, quickly proved to be a profound guide for research in atomic and subatomic physics. Laboratories across Europe and the United States began to design experiments that could probe the boundaries of what could be known, testing the limits of measurement, precision, and observation. Physicists learned to accept that nature itself imposed fundamental constraints, and in doing so, they discovered new ways to explore the quantum world with creativity and rigor. One of the most immediate impacts of the uncertainty principle was on the interpretation of quantum mechanics itself. Prior to Heisenberg, many scientists sought to visualize atomic processes in the same way they could visualize planets orbiting the sun. With uncertainty, this approach was no longer tenable. Instead, physicists began to focus on measurable quantities and the statistical distributions that governed them. The concept of the wave function, which describes the probabilities of a particle's properties, gained central importance. Heisenberg's principle became the bridge between abstract mathematics and experimental reality, providing a framework for understanding why certain outcomes were fundamentally unpredictable while others remained highly probable. The debates sparked by the uncertainty principle were not merely technical, they were philosophical. Albert Einstein, who had been instrumental in laying the foundations of quantum theory, could not accept a universe governed by probability. He spent decades proposing thought experiments designed to demonstrate that quantum mechanics was incomplete, believing that hidden variables might restore determinism. Niels Bohr and Heisenberg, in contrast, defended the principle as an essential feature of nature. Their dialogues, which unfolded in the halls of Copenhagen and in scientific correspondence, became legendary. They argued over the meaning of reality, measurement, and causality, ultimately establishing a philosophical framework that emphasized complementarity, the idea that different, apparently contradictory descriptions could coexist as part of a complete understanding of phenomena. Beyond philosophy, the uncertainty principle had concrete experimental consequences. In spectroscopy, the principle explained the natural broadening of spectral lines, a phenomenon that had puzzled physicists for decades. It clarified why precise measurements of energy levels were always accompanied by corresponding uncertainties in other properties, such as momentum or position. In particle physics, the principle guided the design of experiments that probed subatomic interactions, influencing the development of scattering experiments, particle accelerators, and the detection of fleeting, ephemeral particles that existed only momentarily before decaying. It became a cornerstone for understanding nuclear reactions, electron behavior, and the emerging field of quantum electrodynamics. Technological advancements soon followed from the understanding provided by Heisenberg's insight. The uncertainty principle underpins the operation of modern electron microscopes, which exploit the wave-like behavior of electrons to achieve resolutions far beyond what traditional optical methods allow. It is also foundational to quantum cryptography, where the act of measuring a quantum system inherently disturbs it, providing secure communication channels impossible to eavesdrop upon without detection. Quantum computing, now emerging as a transformative technology, depends directly on the probabilistic and uncertain nature of quantum states, utilizing superposition and entanglement, concepts deeply tied to the principles Heisenberg articulated nearly a century ago. The philosophical impact of the uncertainty principle extended well beyond the laboratory. It forced humanity to reconsider the nature of knowledge itself. Certainty, once assumed to be attainable through careful observation and reasoning, was revealed to be limited at the most fundamental level. Human perception and measurement are inseparable from the phenomena they observe, implying that objective reality is, in some sense, participatory. This insight resonated with thinkers in diverse fields, philosophy, literature, psychology, who found in quantum mechanics a metaphor for ambiguity, interdependence, and the limits of human understanding. Heisenberg himself reflected on these broader implications throughout his life. He wrote extensively about the interplay between science, philosophy, and ethics, emphasizing that the uncertainty principle was not merely a scientific discovery, but a guide to intellectual humility. Understanding the limits of what can be known, he suggested, is as important as the pursuit of knowledge itself. It teaches restraint, caution, and responsibility, particularly in a world where technological power can have profound societal consequences. The uncertainty principle also influenced subsequent generations of physicists, inspiring them to explore ever deeper questions about the structure of matter and the nature of reality. Figures such as Richard Feynman, Murray Gell-Mann, and John Bell built upon Heisenberg's work, extending quantum theory into new domains and exploring its implications for entanglement, non-locality, and the foundations of quantum field theory. The principle's legacy continues to shape research in particle physics, condensed matter physics, quantum information science, and cosmology. As the 20th century progressed, the uncertainty principle became a symbol of the profound intellectual transformations that quantum mechanics had wrought. It highlighted the limits of human knowledge, the participatory nature of observation, and the probabilistic character of the physical world. It inspired debates, philosophical inquiry, and technological innovation, bridging the realms of science, culture, and thought. Heisenberg's insight demonstrated that the act of discovery is inseparable from the limits imposed by the universe itself. Even in contemporary science, the uncertainty principle remains central. Quantum technologies, including computing, sensing, and communication, exploit the very principles that Heisenberg formulated. Researchers continue to test its limits, probing ever smaller scales and ever faster times, revealing new layers of complexity and subtlety. The principle's enduring relevance underscores its foundational role in understanding the universe. In essence, the uncertainty principle reshaped not only physics, but human thought. It challenged the notion that the universe is fully knowable, highlighting the inherent limitations and responsibilities of scientific inquiry. It reminded humanity that while knowledge can illuminate the workings of nature, it can never fully capture the totality of reality. Heisenberg's contribution stands as a testament to the power of imagination, rigor, and philosophical reflection, a bridge between the abstract world of mathematics and the profound mysteries of existence. Ultimately, the uncertainty principle is more than an equation, it is a paradigm, a lens through which to view the universe. It encapsulates the tension between certainty and ambiguity, measurement and influence, knowledge and mystery. It is a principle that continues to inspire, challenge, and guide scientists, philosophers, and thinkers of all kinds, reminding us that the pursuit of understanding is an endless journey, and that in embracing uncertainty, humanity can glimpse the profound elegance of the cosmos. In the years following the establishment of quantum mechanics and the formulation of the uncertainty principle, One of the most compelling areas of exploration became the dual nature of particles and waves, a concept that challenged conventional wisdom and transformed our understanding of the microscopic world. Scientists had long believed that matter and energy occupied distinct realms. Particles had mass and occupied space, while waves carried energy and propagated through mediums. Yet, experiments in the early 20th century revealed a far more complex reality. Electrons, photons, and other subatomic particles exhibited behaviors that were both wave-like and particle-like, depending on how they were observed. This duality was not a mere curiosity, it was a central feature of the quantum universe, forcing physicists to rethink the fundamental principles of reality. The idea of wave-particle duality began to take shape with the work of Albert Einstein on the photoelectric effect in 1905. By proposing that light could be thought of as discrete quanta, or photons, Einstein challenged the classical notion that light behaved solely as a continuous wave. Experimental confirmation soon followed, as the emission of electrons from metal surfaces under illumination could only be explained by assuming that light arrived in discrete packets of energy. This insight not only validated Planck's earlier quantum hypothesis, but also suggested that the classical distinction between waves and particles was incomplete. Louis de Broglie in the 1920s extended this concept to matter itself. He proposed that if light could exhibit particle-like behavior, then particles such as electrons should also exhibit wave-like properties. This revolutionary hypothesis was soon confirmed through experiments demonstrating electron diffraction, where beams of electrons produced interference patterns characteristic of waves when passed through crystals or slits. The notion that particles could behave like waves shattered traditional intuition and provided a deeper understanding of atomic and subatomic phenomena. The dual nature of matter and energy required a fundamental rethinking of measurement and observation. Classical physics relied on visualizable trajectories, precise positions, and predictable velocities. In the quantum realm, however, electrons could not be described as traveling along a single path. Instead, their behavior was represented by wave functions that described probabilities of finding a particle in a particular location. This probabilistic approach was radically different from deterministic models and required the development of new mathematical tools and conceptual frameworks. The experimental verification of wave-particle duality had profound implications. Interference and diffraction patterns, previously associated only with light and other waves, were observed in electrons and other particles. Similarly, phenomena such as the Compton effect demonstrated that photons, traditionally considered waves, exhibited particle-like collisions with electrons. These findings unified the descriptions of matter and energy under the quantum framework and laid the groundwork for the development of quantum field theory, where particles are treated as excitations of underlying fields that possess both wave-like and particle-like characteristics. Wave-particle duality also reshaped the interpretation of atomic and molecular systems. Electrons in atoms were no longer envisioned as orbiting the nucleus in fixed paths, as in classical models. Instead, their behavior was described in terms of standing wave patterns, known as orbitals, which indicated regions of high probability density rather than precise locations. This understanding allowed scientists to predict chemical bonding, molecular structures, and spectroscopic behavior with unprecedented accuracy, bridging the gap between theoretical predictions and experimental observations. Philosophically, wave-particle duality challenged the very notion of reality as it had been understood for centuries. The idea that particles could exhibit complementary aspects, simultaneously embodying contradictory properties depending on how they were measured, called into question the classical assumption that objects possess inherent attributes independent of observation. Niels Bohr introduced the principle of complementarity, emphasizing that wave and particle descriptions are mutually exclusive yet jointly necessary for a complete understanding of quantum phenomena. This concept became central to the Copenhagen interpretation of quantum mechanics, shaping the way generations of physicists approached the study of the microscopic world. The duality also had practical implications beyond theoretical physics. It guided the development of technologies such as electron microscopes, which exploit the wave-like nature of electrons to achieve resolutions far beyond conventional optical limits. Similarly, the understanding of photons as discrete packets of energy enabled the development of lasers, semiconductors, and other devices that form the backbone of modern electronics and communication. The conceptual insights of wave-particle duality directly informed the engineering of technologies that have transformed daily life. As quantum mechanics matured, the dual nature of particles became a central motif in the exploration of the quantum realm. Experiments continued to reveal ever more subtle manifestations of this duality, from quantum tunneling, where particles pass through barriers seemingly insurmountable in classical physics, to interference patterns in larger and more complex molecules. These findings confirm that wave-particle duality was not restricted to light or simple particles, but was a universal feature of matter at the quantum scale. Ultimately, wave-particle duality exemplifies the revolutionary nature of quantum mechanics. It defies intuition, challenges classical assumptions, and reveals a universe where reality is not fixed but context-dependent. It underscores the probabilistic, interconnected, and non-deterministic nature of the quantum world, where observation, measurement, and interaction define the very properties of particles. Through this principle, scientists gained a powerful lens for exploring the unseen realms of matter and energy, unlocking insights that continue to drive both scientific discovery and technological innovation. The exploration of wave-particle duality illustrates the human capacity to embrace paradox and adapt understanding to evidence rather than intuition. It demonstrates the courage and creativity required to rethink fundamental concepts in the face of experimental reality. From electrons to photons, from atomic orbitals to advanced quantum technologies, the duality of particles and waves remains central to our understanding of the universe, a testament to the profound and enduring legacy of the quantum revolution. ChatGPT said following the revelations of quantum mechanics, one of the most transformative insights emerged from the study of atomic and subatomic interactions. The realization that the universe at its most fundamental level operates according to probabilities rather than certainties. Classical physics had long been rooted in determinism, the notion that if one knew all initial conditions, the future behavior of a system could be precisely predicted. However, experiments with electrons, photons, and atomic nuclei consistently demonstrated that such predictability breaks down at microscopic scales. The probabilistic nature of quantum mechanics not only reshaped scientific understanding, but also redefined humanity's conception of reality itself. The principle of probability in quantum mechanics is intimately tied to the mathematical concept of the wave function. Each particle is described by a wave function, a complex mathematical entity that encodes the probabilities of the particle's possible states, such as position, momentum, and energy. Unlike classical particles which follow definite paths, quantum particles exist in a superposition of multiple potential states simultaneously. Only upon measurement does the wave function collapse into a single outcome, an event that appears random yet is governed by precise probabilistic rules. This framework provided scientists with the first consistent way to predict outcomes in an inherently uncertain universe. Experiments in the early 20th century continually confirmed this probabilistic behavior. Radioactive decay, for example, cannot be predicted for an individual atom. Scientists can only calculate the probability that a given atom will decay over a certain period. Similarly, in scattering experiments and atomic transitions, measurements yield distributions of outcomes rather than single, deterministic results. These findings demonstrated that at the atomic and subatomic levels, the universe is governed not by fixed certainties, but by statistical laws that reveal underlying order through probabilities. The probabilistic nature of quantum mechanics also reshaped the methodology of experimental physics. classical concepts such as trajectory and velocity lost their absolute significance. Instead, physicists focused on the likelihood of particular outcomes and the relationships between observables. Tools like probability amplitudes and operators became central, allowing scientists to calculate expectations, variances, and correlations among quantum variables. The shift from deterministic prediction to probabilistic expectation required a radical reconceptualization of both theory and practice. This new framework also had philosophical implications. Determinism, a cornerstone of classical thought, was replaced by a universe in which chance and potentiality are fundamental. The uncertainty inherent in quantum systems suggested that reality is not fully predetermined and that events may occur without deterministic cause at the smallest scales. This challenged long-standing notions of causality and invited reflection on the limits of human knowledge. The probabilistic nature of quantum mechanics emphasized that scientific understanding is not a mirror of absolute reality, but a tool for predicting patterns within the constraints of measurement and observation. Probabilities in quantum mechanics are not merely a reflection of ignorance, but a fundamental aspect of physical reality. The mathematical formalism of the theory demonstrates that even with complete knowledge of the wave function, only probabilistic predictions are possible. This realization has profound implications, influencing interpretations of reality and prompting debates over the meaning of existence and the nature of objective truth. Some interpretations, such as the Copenhagen interpretation, embrace the probabilistic framework as an essential feature of the universe. Others, like the many worlds interpretation, suggest that each possible outcome corresponds to a branching universe, emphasizing the multiplicity of reality in a manner consistent with quantum probability. The probabilistic framework also underpins a host of technological advancements. Quantum mechanics explains the behavior of semiconductors, superconductors, and lasers, all of which rely on probabilistic distributions of electrons and energy states. Modern electronics, quantum computing, and advanced communication systems exploit the probabilistic behavior of particles to achieve functionality impossible under classical deterministic assumptions. Without embracing probability as a fundamental principle, these technologies could not exist. Furthermore, the probabilistic aspect of quantum mechanics fostered deeper collaboration between theory and experiment. Physicists had to refine measurement techniques to capture statistical distributions accurately and to interpret results in light of the wave function formalism. The focus shifted from single events to ensembles, averages, and correlations, highlighting the statistical nature of quantum reality. This paradigm shift not only enhanced experimental design, but also strengthened the connection between abstract mathematics and observable phenomena. Culturally, the embrace of probability resonated with broader philosophical and intellectual movements of the 20th century. It reflected a world in which certainty was increasingly recognized as provisional and contingent, mirroring developments in philosophy, literature, and the social sciences. Quantum probabilities suggested a universe that is dynamic, interconnected, and fundamentally uncertain, prompting humans to reconsider assumptions about causality, prediction, and control. The probabilistic framework thus extended beyond physics, shaping contemporary thought across multiple disciplines. Ultimately, the recognition of probability as a core feature of the quantum world represents one of the most profound shifts in scientific history. It challenges the deterministic worldview that dominated for centuries, replacing it with a framework in which uncertainty, potentiality, and statistical patterns govern the behavior of nature. Through this lens, the universe emerges not as a fixed machine, but as a complex tapestry of possibilities, where the interplay of chance and law defines the structure of reality. The study of probabilities in quantum mechanics demonstrates the power of human intellect to adapt understanding in the face of evidence. It reveals a universe that is both ordered and unpredictable, where the act of observation interacts with potentiality to produce outcomes, and where certainty is replaced by expectation. This paradigm continues to guide research, inform technology, and inspire philosophical reflection, illustrating the profound legacy of the probabilistic insight within the quantum revolution. In essence, the probabilistic nature of quantum mechanics provides a new way to comprehend reality. It challenges classical assumptions, empowers technological innovation, and inspires a deeper appreciation of the limits and possibilities of human knowledge. It remains a testament to the transformative power of scientific inquiry, revealing a universe far richer and more subtle than previously imagined, where probability is not a limitation but a window into the underlying order of existence, ChatGPT said. Following the foundational principles of quantum mechanics, one of the most striking developments in the study of atomic and subatomic physics was the exploration of quantum entanglement and non-locality, phenomena that revealed an interconnectedness in nature far beyond classical comprehension. In the classical view of physics, objects are independent and interactions occur locally. What happens to one object affects only its immediate surroundings. Yet, experiments in the early 20th century and theoretical analyses revealed that quantum particles could become linked in ways that allowed their properties to be correlated instantaneously, even across vast distances. This concept, initially counterintuitive, became a central feature of modern quantum theory, fundamentally challenging assumptions about separability, causality, and the nature of reality itself. The origins of the concept of entanglement can be traced to the thought experiments and theoretical inquiries of the pioneers of quantum mechanics. While quantum theory described probabilities and uncertainties at the level of individual particles, the implications of correlations between multiple particles remained a source of deep investigation. Mathematicians and physicists realized that particles emerging from a single interaction could retain a connection, such that measuring one particle would instantaneously affect the predicted outcome of its partner, regardless of the distance separating them. Albert Einstein, Boris Podolsky, and Nathan Rosen famously articulated this idea in the EPR paradox of 1935, framing it as a challenge to the completeness of quantum mechanics. They were unsettled by the notion that information could seemingly travel faster than light, violating classical expectations of locality and causality. The EPR paradox prompted intense debate among physicists. Niels Bohr, representing the Copenhagen interpretation, argued that the apparent, spooky action at a distance was a reflection of the holistic nature of quantum systems. Particles should not be considered as independent entities with predetermined properties, but as components of a shared quantum state. Measurement, Bohr asserted, cannot be viewed in isolation. It fundamentally alters the state of the system, and any correlations between particles are a natural consequence of their shared quantum history. This perspective emphasized the radical departure of quantum mechanics from classical intuition, reinforcing the idea that the universe at its core is deeply interconnected. Experimental confirmation of entanglement began decades later, with advancements in technology allowing precise control and measurement of quantum systems. Experiments involving photons, electrons, and other particles demonstrated correlations that could not be explained by classical physics. These observations confirmed that entangled particles exhibit outcomes that are interdependent, even when separated by significant distances, defying the assumption that properties are fixed prior to measurement. Such experiments validated the predictions of quantum theory and underscored the revolutionary nature of entanglement. The implications of entanglement extend far beyond the laboratory. Philosophically, it challenges the classical notion of separability, suggesting that parts of a system cannot always be fully understood in isolation. The interconnectedness implied by entanglement hints at a universe where relationships, context, and correlations are fundamental. It forces a reconsideration of the nature of causality, prompting questions about how information is transmitted, what constitutes reality, and how observers interact with the systems they study. This interconnected perspective resonates with broader intellectual currents that emphasize relational understanding and systemic thinking. Entanglement has also driven technological innovation. It forms the backbone of quantum communication, enabling ultra-secure methods of transmitting information through quantum key distribution. In these systems, any attempt at eavesdropping disrupts the entangled state, providing immediate detection of interference. Similarly, entanglement is central to quantum computing, where qubits leverage the correlations of entangled states to perform calculations at speeds and efficiencies unattainable by classical computers. The practical applications of entanglement illustrate how a once purely theoretical insight has become a catalyst for revolutionary technology. Moreover, the study of entanglement has deepened our understanding of the fundamental structure of reality. It highlights that quantum systems cannot always be decomposed into independent parts, and that observation plays a crucial role in defining outcomes. In multi-particle systems, the state of the whole contains more information than the sum of its parts, a concept that challenges reductionist thinking. This insight has profound consequences for fields ranging from condensed matter physics to cosmology, where entanglement influences the behavior of complex systems, from the smallest molecules to the structure of space-time itself. Entanglement also inspired new approaches to experimental design and measurement. Physicists developed sophisticated techniques to create, maintain, and manipulate entangled states, allowing precise testing of theoretical predictions and exploration of phenomena such as Bell inequalities. These experiments have consistently demonstrated violations of classical assumptions, confirming that quantum correlations cannot be explained by local hidden variables. The empirical evidence of entanglement has solidified its role as a foundational principle of modern quantum theory. Culturally and intellectually, entanglement has captured the imagination of thinkers beyond physics. It provides a metaphor for interconnectedness in nature, society, and consciousness, suggesting that the apparent separateness of objects or individuals may mask deeper relational structures. Artists, philosophers, and writers have drawn inspiration from the concept, exploring themes of unity, correlation, and the subtle interplay between observation and reality. Entanglement, in this sense, bridges the realms of science and human thought, offering a profound lens through which to understand both the physical universe and human experience. Ultimately, quantum entanglement and non-locality exemplify the transformative power of quantum mechanics. They demonstrate that at the most fundamental level, reality is not composed of isolated, independent particles, but of interconnected systems whose properties emerge in relation to each other and to observation. These insights challenge classical intuition, expand technological possibilities, and invite ongoing philosophical reflection. Entanglement stands as a testament to the depth, subtlety, and interconnectedness of the quantum world, revealing a universe that is far more intricate and interdependent than previously imagined. The exploration of entanglement continues to shape modern science. From quantum teleportation experiments to advanced quantum networks, researchers are continually uncovering new ways to harness and understand the profound correlations that define the quantum realm. These discoveries affirm that the study of entanglement is not merely an abstract pursuit, but a gateway to practical applications, deeper comprehension, and a reimagined view of the universe itself. It remains one of the most compelling and revolutionary aspects of quantum mechanics, a concept that continues to expand the boundaries of knowledge and challenge our most fundamental assumptions about reality. As quantum mechanics matured, one of its most profound contributions to science and technology emerged from its implications for the practical manipulation of matter and energy at the smallest scales. The development of quantum technologies, from lasers and semiconductors to modern quantum computers, demonstrates how abstract theoretical insights have been translated into concrete tools that reshape society. What began as a pursuit to understand the strange behaviors of atoms and subatomic particles evolved into a revolution in engineering, computation, and communication, illustrating the remarkable interplay between fundamental science and applied innovation. The path from theory to technology was neither immediate nor straightforward. In the early decades of the 20th century, the principles of quantum mechanics were primarily concerned with explaining phenomena that classical physics could not, such as atomic spectra, electron behavior, and the interactions of light and matter. However, as researchers delved deeper, they began to see that the probabilistic, wave-like, and entangled nature of particles could be harnessed for practical purposes. The development of semiconductors, for example, relied on an understanding of how electrons occupy energy bands within solids, a concept rooted directly in quantum theory. By manipulating these energy levels, engineers could design materials that controlled electrical conductivity with unprecedented precision, forming the foundation of modern electronics. Lasers provided another striking example of quantum principles applied to technology. The concept of stimulated emission, predicted by Einstein, explained how atoms could emit coherent photons when excited. By carefully controlling populations of atoms and energy states, scientists created devices capable of producing intense, coherent beams of light. Lasers transformed countless industries, from medicine to telecommunications, demonstrating that the seemingly abstract mathematics of quantum mechanics could lead to tangible, transformative tools. The development of quantum computing represents perhaps the most ambitious and futuristic application of quantum theory. Unlike classical computers, which rely on bits that are either 0 or 1, quantum computers use qubits that exist in superpositions of states. These qubits can become entangled, allowing information to be processed in ways that classical systems cannot match. The result is the potential for computational speed and efficiency far beyond current capabilities, enabling solutions to problems in cryptography, materials science, and complex simulations that were previously intractable. Quantum computing illustrates how principles such as superposition, entanglement, and probability, once considered purely theoretical, can be harnessed to revolutionize technology. Quantum technologies have also transformed communication and security. Quantum key distribution uses the principles of entanglement and measurement uncertainty to create communication channels that are fundamentally secure. Any attempt to intercept or observe the transmitted information inevitably disturbs the quantum state, alerting the communicating parties to the intrusion. This application demonstrates how the probabilistic and interconnected properties of quantum systems can be exploited to address real-world challenges, from secure data transmission to national security concerns. In parallel with practical applications, quantum technologies have continued to deepen scientific understanding. Tools such as scanning tunneling microscopes and quantum sensors allow researchers to probe matter with extreme precision, revealing phenomena at atomic and subatomic scales that were previously inaccessible. These technologies not only confirm theoretical predictions, but also uncover new phenomena, creating a feedback loop in which theory informs experimentation and experimentation drives theoretical refinement. The synergy between knowledge and application exemplifies the profound impact of quantum principles on the evolution of modern science. The philosophical implications of quantum technologies are equally striking. They reflect a universe in which observation, interaction, and manipulation are inseparable from outcomes. By learning to control quantum states, humans demonstrate that the universe's probabilistic and interconnected nature can be directed toward purposeful ends. At the same time, these technologies remind us that fundamental uncertainty remains intrinsic. Even as we harness quantum phenomena, we must operate within the constraints imposed by nature itself. The duality of control and uncertainty lies at the heart of modern quantum engineering. Education and collaboration have played central roles in the rise of quantum technologies. Institutions worldwide have invested in training scientists and engineers to work at the frontier of quantum mechanics, creating interdisciplinary teams that combine physics, mathematics, computer science, and engineering. International collaborations have facilitated the sharing of ideas, experimental techniques, and theoretical advancements, accelerating progress and enabling breakthroughs that would have been impossible in isolation. This collective effort reflects the global significance of quantum technologies and their potential to transform both knowledge and society. The impact of quantum technologies extends beyond laboratories and industrial applications. They inspire new ways of thinking about information, computation, and the nature of reality itself. Concepts such as entanglement and superposition, once abstract mathematical constructs, have become tangible tools that reshape industries, economies, and scientific paradigms. In doing so, they illustrate the remarkable journey from curiosity-driven research to practical innovation, highlighting the transformative power of fundamental science when coupled with ingenuity and vision. Ultimately, the development of quantum technologies underscores the enduring legacy of quantum mechanics. It demonstrates that understanding the behavior of matter and energy at the smallest scales is not merely an intellectual exercise, but a gateway to practical solutions and revolutionary tools. Lasers, semiconductors, quantum computers, and secure communication systems all trace their origins to the principles first articulated by pioneering scientists exploring the mysteries of the atom. These technologies embody the synthesis of theoretical insight and practical application, showing that the quantum revolution is not confined to equations on paper, but is reshaping the world in profound and lasting ways. The story of quantum technologies also serves as a reminder of the interplay between curiosity, imagination, and rigorous inquiry. It is a testament to the human drive to understand, explore, and harness nature, even when its principles defy intuition. By translating the abstract laws of the quantum world into tools that enhance human capability, scientists and engineers have created a bridge between knowledge and action, theory and practice, revealing both the power and the subtlety of the universe. In this sense, quantum technologies are not only instruments of progress, but also symbols of human ingenuity, perseverance, and the enduring quest to illuminate the hidden structures of reality.